Hi everyone. For our capstone project, we're going to be interpreting a state geological map of Oregon. The first region we're going to start with is the Coast Range of Oregon. In the southwestern corner of the map, there's a portion of the coastal ranges mostly shown in green, which show different types of terrains. Because these terrains were either too big or too thick to easily slide beneath the edge of the North American continent, they remained in the subduction zone and welded themselves to the edge of a growing plate called the Juan de Fuca Plate. In this area, there are also a variety of moraine rocks from the Jurassic period, which include mafic volcanic rocks, marine mudstone, sandstone, serpentinite, chert, and blue schist, which travel down in the subduction zone. To the west, the tectonic collision forced sedimentary rock formations that include marine terrace deposits from the Eocene age. These rocks include marine sandstone, conglomerate, shale, and siltstone. Many of these sediments were deposited below sea level but have been uplifted by ongoing compression from the convergence. Towards the northwestern region, it includes normal and reverse faults with a strike going from west to northwest. Starting with the northern part, this area also includes northward plunging anticlines and includes volcanic rocks from the lower to middle Eocene age. Much of these formations are the result of pillow basalt formations created when a hot basalt flow rapidly cools upon meeting the salt water of the ocean. The next area we're going to cover is the Columbia River Plateau, which is along the northern half of the coast in orange. In the north, there's a large amount of lava called the Columbia River basalt that flowed west. These volcanic igneous rocks were from fissure eruptions as the continent overrode the Yellowstone hotspot during the Miocene time. As the Columbia River basalt cooled, it also created columnar cliffs. As the molten rock came to the surface, the Earth's crust gradually sank into the space left by the rising lava. This part of the crust produced a large, slightly depressed lava plateau. Around the edges of the large area covered by flood basalts, you could see some of the older rocks that were covered by the lava flows. Because of the depressed lava plateau, the ancient Columbia River was forced into its present course by the advanced lava that came from the northwest. In the western and central parts of the Columbia River basin, it also consists of a series of anticline ridges and sinocal valleys. In terms of the ages of the rocks, the youngest were clustered near the Yellowstone Plateau, and the further west they went, the older they were.
Most of the exposed rocks from this area are from the Cenozoic period, so I have a little equation just so you get a sense of the time, right? So the Cenozoic era encompasses the Tertiary period, and the Tertiary period is composed of the Paleogene plus the Neogene era, as you can see from the geologic timescale to the right. And also, the Paleogene encompasses the Paleocene plus the Eocene plus the Oligocene. And so if I were to say that volcanism began in the Paleogene, you would understand that it would start around the Paleocene or the Eocene or the Oligocene. The basin of range is the area of faulting and a lot of ridges that took place in the Neogene. Volcanism began during the Paleogene period around the Eocene epoch, and the basin of range formed during the Miocene. Rocks here include a lot of basalt and andesite, igneous rocks associated with the volcanism. But there were episodes of sedimentary rocks, such as in the Pleistocene period, where you see fluvial sedimentary rocks, siltstone, sandstone, gravel, and in certain places you see fossils of mollusks, indicating that Pleistocene age. Keep in mind that this is a rough estimate as to where exactly the basin of range begins and ends. But with that being considered, here is the age and composition of the rocks. Most of the rocks in the basin of range are from the Miocene to the Pleistocene range. The oldest rock from the basin and range is labeled TSF, and it's from the Lower Miocene era, Lower Miocene period, and it's composed of rhyolitic tuff, medium grain tuff, and clay minerals. It also has fossil plants indicating the Oligocene and the Miocene age. It includes the Pike Creek Formation and is colored light green, blue on the map. You have a layer color coded in brown. It's called the TBA, and it includes lava flows and breccia. Contains basalt and andesite, and it also includes sedimentary rocks which contain vertebrate fossils from the Miocene. The TVS layer, which is white colored with red dots, and it is found in the Pliocene, the Miocene, the Oligocene, and also the Eocene. It contains rhyolite, breccia, obsidian, perlite, and pumice. The next group is labeled TVM, and it's purple with triangles. It is from the Pliocene age or the Miocene, and it includes rocks, basaltic rocks, andesite rocks, andesitic agglomerate, breccia, scoria, cinders, and flows. We have the yellow colored rock, which is labeled QS, and it includes equestrian and fluvial sedimentary rocks. It is from the Pleistocene age, and it's composed of silt, sand, and gravel. Certain places contain fossils such as mollusks, indicating the Pleistocene age.
The area I'll be covering is the Cascadian Range. The subduction of the Juan de Fuca Plate, a lot of volcanism occurred. The youngest rock is going to be labeled as QYB and was deposited in the late Holocene. The oldest rocks, which were deposited in the Oligocene and the Upper Eocene, are labeled as TFE, TFEE, and TFEB. Layers TFE and TFEE are marine sediments, a part of the Eugene and Fisher formations. They are made up of coarse to fine-grained Arcosic and Micaceous sandstone and siltstone, though these layers are rarely visible due to the basaltic flows and ash flows that overlay them. The first formation we're going to be looking at is going to be in the center of the Cascades, which contains some of the older volcanic formations. Davis Lake is to the south in this image and contains a volcanic field. The round purple formations of the layer QT and V are shield volcanoes formed in the Pleistocene and Miocene. Examples on this image that are visible include Lookout Mountain, Pelican Butte, Bachelor's Butte, and Maiden's Peak. To the north of Davis Lake, there's a layer QA in red. QA is mainly made up of andesite, and is from the Pleistocene to early Holocene. This andesite forms stratovolcanoes, and the stratovolcanoes we see here are known as the Three Sisters. Although these volcanoes ceased activity in the late Pleistocene, basaltic to rhyolithic vents erupted in the late Holocene, producing lava flows in the rock layer QBA around the Three Sisters, and rhyolithic lava domes and flows to the south in layer QRD. And you can see one of those lava flows here in the bottom left corner of this picture. You may have noticed some strange things happening in this map. These little purple blotches you see all over the map, they're actually basaltic and andesitic ejecta coming from the stratovolcano. And to the west, in layer OG in yellow, it actually gives us a brief break in talking about volcanism, as these are unsorted glacial deposits. To the west of Waldo Lake, as the glacier receded, you could see that it left behind little moraines and dendritic drainage, along with the telltale of a glacier of the U-shaped valley over here. Next, we'll be moving to the south and looking at Crater Lake. Crater Lake is a caldera, formed from the collapsed composite volcano of Mount Mazama. To the northeast of the crater, in layer QMA, are ash flow deposits, and to the southwest, in layer TRB, are lava flows of breccia and basaltic andesite, and finally, to the east, in layer QRD, are domes and flows. And just as the previous slide, the layer QTP in purple are basaltic and andesitic ejecta coming from the eruptions of Mount Mazama. Moving just north of the Three Sisters, we have Mount Jefferson. Mount Jefferson is the second tallest mountain in Oregon, standing at 3,199 meters tall. It was a stratovolcano and is surrounded by lava flows. Some of these lava flows we can see here are layer TFC in black, which are flows in clastic rocks, TRB, which we saw in previous formations, and TBAA, which are basaltic and andesitic lava flows. And lastly, to the north of Mount Jefferson, we have Mount Hood. Mount Hood is the tallest mountain in Oregon, standing at 3,429 meters tall. Although informally considered as dormant, it is the Oregon volcano most likely to erupt, with chances between 3 and 7% in the next 30 years. Because of those chances, the USGS characterizes it as a potentially active volcano. You can actually see a little bit of the youngest rock flow, layer QYB, in the southwest in pink over here. And Mount Hood is also surrounded by a ton of lava flows. It is surrounded by layer TFC, TRB, TBAA, and QBA to the north. You can also see some large exposed dikes and stacks of hornblende diorite and quartz diorite in layer THI.